This video is just going to cover some of the basic functional groups that you're going to come across in our first year organic chemistry module and throughout your degree. So what do we mean by a functional group? Well, basically it's just a conserved arrangement of atoms shared across multiple molecules which have similar properties and impart similar patterns of reactivity. So for instance, if we were to look at this molecule here, we can identify certain functional groups in this molecule. I've just highlighted one in purple. So if we were to react this with another molecule which had a different functional group in it, we might produce a product which had a third functional group in it. So what this allows us to do is to identify that the part of the molecule which is important for a reaction to occur is the functional group. It doesn't matter so much what the rest of the molecule is if you can identify the functional groups. So that when we get on to looking at different molecules, if we can identify the same functional group in that molecule and react it in a similar way, you might expect to get a similar product. So you're not having to memorize chemical reactions as a reaction of chemical A with chemical B to give chemical C. If you understand chemical reactions in terms of functional groups, so the reaction of functional group A with functional group B gives functional group C, then it becomes a lot more ubiquitous and it allows you to predict chemical reactivity essentially, even in molecules you've never seen before. So the other thing that functional groups allow us to do is to interpret organic molecules in a kind of conserved and concerted way. And it also helps to simplify things a bit. So I always like to say that organic molecules are essentially functional groups held together by grease. So functional groups held together with alkane hydrocarbons. So if we look at a kind of scary looking complex molecule like this is Taxol. If we actually break it down and we look at all the functional groups and highlight them in purple, it doesn't look so bad because now you can start to identify parts of the molecule that you think will behave in certain ways. And the rest of it is just alkane hydrocarbon chains. So in this module we're going to come across a number of functional groups and I've categorized them. So basically I've categorized them by what atoms are present in there, so whether they've just got carbon and hydrogen in, whether they're oxygen containing, nitrogen and oxygen, or whether they've got halides in there. And I've also categorized them as to whether they've got a carbonyl in there or not. So you can't see underneath this big X, but a carbonyl is a carbon-oxygen double bond. So the presence of the carbonyl changes how the functional group behaves. It also changes how we classify them. So I've dealt with them both separately. So with just the hydrocarbon-based functional groups, we're going to deal with alkenes, alkynes, and benzene. Obviously, there aren't any carbonyl-containing functional groups with just carbon and hydrogen in because there's an oxygen here. On the oxygen side of things, we're going to come across alcohols, ethers, and epoxides. And then carbonyl-containing functional groups, aldehydes, ketones, carboxylic acids, and esters. In terms of the nitrogen-containing compounds, amines and nitriles. And obviously, again, because carbonyls have got oxygen in, we can't have any functional groups that have just got nitrogen in. And then for nitrogen and oxygen, we're going to come across nitro and amides. And then with halides, alkyl halides, aryl halides, and acyl halides. So these are all the functional groups we're going to cover in the first year module. They're probably the most common functional groups that you'll come across in organic chemistry in general. But obviously there are a lot more out there that are variations on the theme or slightly more complex. So starting with alkenes. Alkenes are basically a carbon-carbon double bond. So if we look at all these molecules here are some real-life examples. I've just highlighted the alkene functional group in purple. So alkenes commonly display cis-trans isomerism or geometric isomerism because anywhere you've got a double bond, this is the presence of a pi bond, which you'll come across if you watch the videos on molecular orbital theory. Whenever you've got a pi bond here, the bond can no longer rotate. So you can actually get geometric isomers, like over here we have butene, this is cis-butene, and this is trans-butene. They are completely different compounds, they have different properties. A special case of alkenes, if you like, is if you have three alternating carbon-carbon double bonds in a six-membered ring, and this is benzene, or a phenyl ring, if you like. So benzene itself is the unsubstituted compound shown here, which is used as a solvent. But it's really, really commonplace to have this functional group present in organic molecules in general. So the reason we've separated these two out is because the carbon-carbon double bonds in benzene behave differently to isolated alkenes. So they react in different ways. They're generally less reactive. But we'll come across a number of reactions in this module which deal with both. So in terms of abbreviations, if you have a benzene ring as part of a molecule and it's otherwise unsubstituted, it's just connected to the molecule, this is a phenyl group, which is abbreviated as PH. If you've got some other substitution pattern on this benzene ring, so here we've got this hydroxyl group and a bromine, you can abbreviate this as an aryl group, but obviously then you're losing some structural information. So if you're abbreviating as an aryl group, you usually have to define what it is. So onto alkynes. Alkynes are a carbon-carbon triple bond. So here are some examples of alkynes, and I've just highlighted in purple the alkyne functional group. So alkynes which end a chain, this is just a nomenclature issue, are called terminal alkynes. So for example, this alkyne over here would be a terminal alkyne. This alkyne over here is a terminal alkyne. All the other ones here are internal alkynes. Note the bond angles, which are 180 degrees, because alkyne carbons are sp hybridized, so we should reflect the geometry of the actual molecule. So the bond angles to a triple bond are 180 degrees, and I'll discuss this in a number of other videos. Alcohols are a carbon with an OH group attached, providing that the carbon does not also bear a carbonyl. Okay, so a carbonyl functional group, just as a reminder, is a carbon-oxygen double bond. So this carbon here cannot also have a carbonyl on it if you want it to be an alcohol. So here are some examples. We've got ethanol, propanol, isopropanol, and so on. These are all alcohol functional groups, and I've just highlighted that in purple. But if we look at this compound over here, the carbon where the OH group is attached also has a carbonyl on it, right? So this is not an alcohol. We'll come on to what that is later on. So there is a classification system for alcohols. We've got primary alcohols, which is these two over here, secondary alcohols, tertiary alcohols, and phenols. And the way that we're classifying these is that primary alcohols have 2 or 3 adjacent CH bonds. So the carbon, which has got the OH group attached, has either 2 or 3 hydrogens attached to the carbon. Obviously, if it's got 3 hydrogens attached to it, that's just one compound, which is methanol. Secondary alcohols have 1 adjacent CH bond at this position here. Tertiary alcohols don't have any. And then phenols, which are kind of a subclass of tertiary alcohols because they don't have any hydrogens here either, but phenols have oxygen directly bonded to a benzene ring. And again, we do that because phenols behave differently from tertiary alcohols. So throughout your degree, you'll come across various chemical reactions involving alcohols, and this is why we make the distinction now, because the primary, secondary, tertiary phenol distinction is important in certain cases. So on to ethers. Ethers have a carbon-oxygen-carbon group, providing that neither of those carbons also bears a carbonyl. So remember, carbonyl, carbon-oxygen double bond, we can't have that on either of these 2 carbons here, otherwise that's not an ether. So here are some examples of ethers. I've just highlighted the ether functional group again. Again, just to reiterate, neither of the carbons can have a carbonyl on it because this functional group here is not an ether. So ethers, straight chain ethers and large cyclic ethers like this are generally unreactive, and a lot of them tend to be volatile, so we use them as lab solvents. So things like THF and dioxane are really common lab solvents because they're inert, unreactive, they don't interfere with the reaction you're trying to do. There is a special case of ethers though, which is that if you've got a 3-membered cyclic ether, they are reactive, and these are called epoxides. So compounds like this, where you've got what you would otherwise classify as an ether, carbon-oxygen-carbon linkage, but it's in a 3-membered ring, these are epoxides, and these are reactive because there's ring strain within this 3-membered ring, so they like to pop open. But we'll cover reactions involving epoxides throughout the module. So moving into the nitrogen section, this is amines. So amines have basically a carbon-nitrogen bond where there's some kind of substituent on the nitrogen, or not, it might just be hydrogen. Again, providing that none of the substituents on the nitrogen can bear a carbonyl, because that's not an amine. So here are some examples, and I've just highlighted the amine functional group. Once again, can't have a carbonyl here because that is not an amine functional group. We'll deal with all of the carbonyls later. So similar to alcohols, amines have a classification system. So we have primary, secondary and tertiary amines, but it works slightly different from the alcohols. So on the alcohols, we were looking at how many hydrogens were attached to the carbon. With amines, we're looking at how many hydrogens are attached to nitrogen. So primary amines have 2 NH bonds. So you can see the substitution changes across all 3 of these compounds at the carbon. Right, this has 2 CH bonds, this has 1, this has none. They're all primary amines because they've all got 2 NH bonds. Okay, so don't get confused between the way that this works and the way that alcohols are categorized. So no prizes for guessing. Secondary amines have 1 NH bond and tertiary amines don't have any. Amines are pretty abundant in nature. You come across a lot of natural compounds which have amines in them, and there's a wide range of biological properties, so they're really abundant functional groups. So a nitrile is a carbon-nitrogen triple bond as part of a molecule. So here are some examples. Some of them are abbreviated, some of them aren't. So some of them I've drawn out, some of them I've abbreviated as CN. That's perfectly fine. So nitrile groups, as I say, can be abbreviated as CN. The old name for nitrile is cyanide. You sometimes use them interchangeably, but it depends on the application. So sodium cyanide, we obviously tend to call sodium cyanide because it's really toxic, quite dangerous. But other things like nitrile rubber, which is used in lab gloves, you probably wouldn't want to advertise your lab gloves as being made of cyanide because it might freak people out. But the two tend to be used interchangeably. Generally, you tend to call them cyanide when they are toxic because that will obviously present an issue and it'll warn people. So like an alkyne, nitrile has bond angles of 180 degrees, okay, because it's sp hybridized. So again, make sure that your chemical structures, your skeletal structures are linear whenever there's a nitrile involved. So moving on to the groups which have both nitrogen and oxygen in, from nitrile to nitro, which is an NO2 group. So here's a load of compounds that have got an NO2 group in them, just highlight them all. So you can either draw it out like this, or you can abbreviate it as NO2. Having multiple nitro groups in a small molecule tends to make it explosive. So anything with a high nitrogen to carbon ratio tends to be pretty pokey. So things like nitroglycerin and TNT are obviously contact explosives. We'll come on to resonance later in the module, but this is a good example of resonance early on. So a nitro group is an average of the 2 resonance forms. So actually, if you push this lone pair of electrons off of oxygen to form a new pi bond with the nitrogen, and then you break this other nitrogen-oxygen bond, you end up with the resonance form, which is this over here. And this is a resonance arrow between the 2. But there'll be an entire section on this later in the module. And we get back to the original resonance form just by using those arrows there. So onto the halides. Starting with alkyl halides, we have a CX group, and X is a common abbreviation for halides. You sometimes see them as C-hal as well. But what do we mean by a halide? Well, if we look at the periodic table, then we have group 17 over here, this column down here. This is the halides. So fluorine, chlorine, bromine, and iodine are the most common ones that you'll come across. So whenever anyone refers to a halide, it's one of those 4 elements. So alkyl halides have a CX group, again providing that the carbon doesn't also bear a carbonyl because that makes it something else. So I've presented a range of different examples here with all the different halides involved, so you can see the range of what's going on. You can also refer to them as their specific names. So this is an alkyl fluoride, this is an alkyl chloride, this is an alkyl iodide, and so on. Once again, just to reiterate, carbonyl changes everything. So this is not an alkyl chloride or an alkyl halide. All right? We'll come on to what this is later on. So like alcohols, there is a classification system, and like alcohols, it works in the same way. So we're looking at the number of CH bonds which are present on the carbon that the halide is attached to. So we've got primary, secondary, tertiary, and aryl halides, and this is classified by having 2 or 3 adjacent CH bonds, 1 adjacent CH bond, none, or in the case of aryl halides, you have no adjacent CH bonds, but your halide is directly connected to a benzene ring. So once again, the distinction is important, and we'll do a lot of reactions in this module, particularly SN1 and SN2 type reactions, where the distinction between these primary, secondary, tertiary designations is really important. So here are just some real life examples. Again, they are hugely diverse, tend not to be found as much in nature because they tend to be either chemically reactive or just unnatural, but really prevalent in organic compounds. So that covers our carbonyl absent functional groups, if you like, the ones that don't have the carbonyls in. So what we'll do now is we'll cover all of the functional groups that have got carbonyls in, and you'll see that they're basically derivatives of these compounds over here just by adding a carbonyl for the most part. So we'll put the carbonyl front and center, and then I'm just going to tell you what it's flanked by. So in contrast to the previous section, the carbonyl is now the focus, and that's not by accident because the carbonyl is really important. It's probably the most important functional group in organic chemistry, so much so that we'll do an entire module or an entire third of a module on it in second year. So a carbonyl flanked by a carbon and a hydrogen, or two hydrogens, although that just gives you one compound, which is formaldehyde, is an aldehyde. So you can think of aldehydes as terminating chains, if you like. They always appear at the end of a chain because obviously you've got hydrogen on one side, so you can't form any additional bonds. The abbreviation is CHO, so you quite often see that used as an abbreviation in skeletal structures. But it's not too arduous to draw it out. Again, you can draw out the hydrogen for clarity, or you can leave it as implicit, as we will discuss in the skeletal structures video. So aldehydes are really useful synthetic intermediates because they're quite reactive. But a lot of them are used in flavourings and fragrances because they tend to be volatile and they add interesting aromas or flavours to various things. So a sort of derivative of the aldehyde, if you like, if you've got a carbon on either side of your carbonyl, that's a ketone. So aldehydes and ketones tend to be grouped together. And you can think of them that way. So because a ketone is flanked by two carbons, ketones tend to appear in the middle of a molecule, in the middle of a chain, whereas an aldehyde is obviously at the end of the chain. So again, broadly ubiquitous, across nature and synthetic chemistry. Again, used in a lot of flavors and fragrances and that sort of thing. And their reactivity is very similar to aldehydes. They tend to be slightly less reactive just because they're bigger. So a carbonyl that's flanked by a carbon, usually, or a hydrogen and an OH group. Again, if it's a hydrogen and an OH group, that's one compound, which is formic acid. But usually if it's a carbon and an OH group, that's a carboxylic acid. So loads and loads of examples of this. These are really prevalent in nature. As the name suggests, they are acidic. And they are substantially less reactive and substantially differently reactive to aldehydes and ketones, but we'll come on to the chemical reactions later on. Abbreviation is CO2H, and you'll see that commonly used all over the place because we're now starting to get quite large functional groups. So a carbonyl flanked by either a carbon or a hydrogen and an OC group is an ester. And esters are derivatives of carboxylic acids. They're commonly made from them. So the abbreviation here, CO2R, you can abbreviate however you wish. So here's a really highly abbreviated example. Again, they're common fragrance molecules, a bit like aldehydes and ketones. But the ester linkage is less reactive, so they tend to be a bit more stable, a bit less pokey. But once again, broad range of biological activities. And as we'll see throughout the module, these are derivatives of carboxylic acids. So by reacting a carboxylic acid with an alcohol, you can make an ester. So this is one of the core reactions that we'll be studying in this module. So the nitrogen derivative of an ester, if you like, is called an amide. So basically the same idea as an ester, just rather than having an oxygen on one side and a carbon on the other, you've now got a nitrogen on one side and a carbon on the other. And amides are absolutely everywhere in nature because peptide backbones, what you call a peptide linkage, is actually an amide functional group. So all of your peptides, proteins, enzymes, all of that kind of stuff are all made of amide linkages. So they've got a nomenclature system similar to amines. but obviously like slightly adjusted. So you're looking at the NH bonds again, but primary amides have 2 NH bonds. So for example, this one over here, NH2. Secondary amides have 1 NH bond. So all of these ones over here are secondary amides. And tertiary amides have none. So this one over here is a tertiary amide. So primary amides tend to be made from ammonia, NH3. Secondary amides tend to be made from primary amines, and so on and so forth. So finally, a carbonyl flanked by a carbon and a halogen, or an X group, is an acyl halide. So contrast that with alkyl halides. As soon as you add the carbonyl, it becomes an acyl halide. They're sometimes called acid halides. I tend not to call them that because it causes a bit of confusion with carboxylic acids. So you tend to refer to these as their parent halides, so acyl fluorides, chlorides, and so on. Chlorides are by far the most common. You might come across acyl bromides or acyl fluorides, but by and large, acyl chlorides are by far the most common acyl halide functional group that you'll come across. They are highly reactive, so they're basically never found in nature. So they're useful as synthetic building blocks because of that reactivity. So as an example, acetyl chloride down here, we saw this at the beginning of the video. It's a useful lab reagent, but it doesn't really tolerate being around water because they are so reactive that they hydrolyze on contact with water to carboxylic acids. So if you were to take acetyl chloride and expose it to water, basically what you would get is displacements of the chloride with OH, which has come from the water, and you've then got a carboxylic acid instead of the acetyl chloride. So just to summarise, these are all the functional groups that we've covered in the video, categorised by whether they've got a carbonyl or not. So we came across alkenes, benzene, alkynes, alcohols, ethers and epoxides, amines and nitriles and nitro groups, alkyl halides and aryl halides. And then in the carbonyl functional groups, we discussed aldehydes, ketones, carboxylic acids and esters, and then amides and acyl halides. So you'll come across these functional groups throughout this module and throughout your degree, and we'll get into how the chemical reactions work with them and that sort of thing as we go through. But you should be able to identify these functional groups as part of organic molecules as a core skill in this module.